Sure. Hi everyone. Welcome to Machine Learning with Python, Advanced Machine Learning 6.3, for the PGD course organized by Emerging Open Tech Foundation. Welcome, and Jamie Tosava, our lead, will be helping deliver this session, and it will cover the advanced topics in machine learning. Thank you. I will hand over now to Jamie to carry forward the presentation. Go ahead, Jamie.
So thanks for the introduction, and welcome everyone for the machine learning with Python. This is session 6.3, and we will be continuing the advanced machine learning topic that we have been covering from session 6.1 and 6.2. So let's get started with session 6.3. So advanced machine learning algorithms. So in this session, we'll be taking help of the binary classification, and then we'll be exploring the K Nearest Neighbour random forest and the boosting techniques. So for understanding these algorithms, we'll be taking help from the bank marketing data set that we have used before, where for the bank's marketing data set is about the campaign that is launched by the bank for the deposit term plan that they have launched. So what we have to predict is whether the customer will subscribe to the plan or not. So first reading the data set, then printing a few of the first 5 observations of the data set, and printing or getting the information about the DF or the data frame of the data set. So you can see that there are 4,521 entries, and there are 11 columns. The data types that are present are integer and the object data type. Object data types are nothing but the categorical data that is present in the data set. Then there is a memory usage being displayed as well. So dealing with imbalanced data sets. So why we say that there is an imbalance in the data set? Because when we say the subscribed, which is the column in the data frame, and the value counts, it shows the yes and no, means that who subscribed and who didn't. So the no's of the dataset are in 4,000, whereas the yes in the dataset are only 521, which makes it an imbalanced dataset. And imbalanced dataset does not help us make a good and reliable model, because it creates its own bias for predicting, and it does not makes it which does not makes it a reliable model. And you can see in the second point as well that even if the model predicts that no customer will subscribe, it will have an accuracy of more than 88%, which is called an accuracy paradox. So going with these values of no's and yes, we will have an accuracy paradox about the model. So let's see how we can deal with the imbalanced data sets. So one approach to deal with, so there are two approaches to deal with imbalanced data set. One is upsampling and another one is downsampling. Upsampling is nothing but increasing the minority up to a certain point. And sampling with replacement is used for this purpose and is also called oversampling. Next is a downsampling, which is reducing the majority, which is no for us in this data set up to a certain point. So reduce the instance of over-represented majority class by removing the existing observations from the data set and is also called undersampling. So to deal with imbalanced data set, the scikit-learn's utils module give us the resample method, and it takes three parameters. The first is the original set itself. Next is the replace, which is it implements a resampling with a replacement, which basically means that the data can be reused if set it to true. So if false, all the resampled examples will be unique. Then number of samples or n samples. So when we get the resample from the sklearn.utils and then use it on our bank DF with no's being saved into bank subscribed no and bank subscribed yes for yes, then re, uh, resampling those data and creating a DF called a DF minority upsampled. So, so in this, we are upsampling rather than downsampling and creating a new DF called new bank DF and concatenating the bank subtype no and DF minority upsampled. So after upsampling, the new bank DF contains 4,000 cases of subscribed equals to no and 2,000 cases of subscribed equals to yes, which makes it the ratio of 67:33. So because the sklearn.util has been used for the resample, we also want to make sure that the data does not appear in a particular order. So we will use the shuffle method on our a new bank DF and then create the X features using the new bank DF and remove the substrate problem from it because that's what we are trying to predict. So the list of X features are listed as you can see: age, job, marital, education, default, all the way till previous campaign. Now, as there are categorical categorical data types, so we have to convert those data types into dummy variables, or we have to one-hot encode those categorical features. So the encoded bank DF will be saved into the pd.get dummies, which are just a one-hot encoded features, and then making the encoded bank DF as our X features. The Y feature is nothing but the subscribed subscribed column. So after that, we will be splitting the data set into the 70-30 ratio with a random seed or random state number of 42 or random state value of 42. So first we'll be creating the logistic regression model, which is a classification model. So the cost function of the logistic regression model is called a log loss or log likelihood or the binary loss function, which is given by the mathematical repression minus 1 by n for summation of I equals to 1 to n yi log pi plus 1 minus yi log 1 minus pi. where Pi is nothing but the probability that Y belongs to a class 1. The probability is given by E equals to Z, e raised to Z by 1 plus E raised to Z, where Z is nothing but the logistic regressions, which is a beta 0 plus a beta 1 x1 plus beta 2 x2 till beta m xm, where x1 to xm are features. So the using the scikit-learn's linear model to import the logistic regression and building our own model logic using that and fitting the model, then making the predictions and on the test X for the predictions of Y. After that, we'll be also creating a confusion matrix. So this will be a custom method that will be used, that will be using for draw CM. So the confusion matrix will be used throughout this session. So this will be the a custom method that we'll be using for creating the confusion matrix for further discussions as well. So we'll be using the matrix.confusion matrix for actual and the predicted values and the labels of 1 and 0. Then using the Seaborn for creating the confusion matrix or creating the heat map to be specific and giving the or assigning the appropriate labels to it. So using the draw CM on our test Y and the prediction Y values, this is the confusion matrix that we get. So you can see that we have high values for the false positives and the false negatives over here. So we'll be creating the classification report using the matrix. So so when we get the classification report for our model, you can see the recall value is really low, which is 0.25, and other values are also low. So to improve those classification reports and to see further for measuring the accuracy of the model. So first we will be using the ROC, which is the receiver operating characteristic and the area under curve score. So ROC, AOC has been used before also in previous sessions. So they are the two important measures of model performance for classification problems. And we'll be using the model's predict probability method, which gives the predicted probabilities for the text examples and can be passed to ROC AOC score along with actual class labels to obtain AOC score. So you creating a predict probability DF and printing a few of the observations from it. You can see the screenshot of or the image on the top right for the class 0 and class 1. So initializing the data frame and assigning the respective probability values for the class label in 1 in the test result DF. Then calculating the ROC AOC score of on the test result DF. with the actual ones and the predicted ones, we get the output of 0.7. So for plotting the ROC curve, we'll create a custom method called a draw ROC curve, which will return the AOC curve, false positive rate, true positive rate values from different thresholds ranging from 0.0 to 1.0. So the parameters that the method will take is the model itself, the test X or the X features of the test set and actual labels of the test set, and it will return the ROC AUC curve or the score, and the FPR and the which is the false positive rate and the true positive rate for the different thresholds values. So defining the draw ROC curve, this is the draw ROC method that we have created and will be using throughout this session. So using the actual and the predicted values on it, then selecting the probabilities that the test example belongs to class 1, invoking the ROC curve to return the false positive, true positive, and the threshold values. The threshold values contain or the thresholds that we have discussed already is from 0 to 1. Then getting the score by invoking the matrix of the Sykitleraning matrix dot ROC AOC score, and then plotting the the values for the respective labels and also assigning the labels as well. So when we draw the ROC curve, this is the curve that we get, and we get the AOC score of 0.70. Now we'll be discussing the K nearest neighbor algorithm. So there are two types of models or algorithms, which are parametric and non-parametric. So K nearest neighbors is a non-parametric algorithm, a lazy learning algorithm used for regression and classification problems. K in KNN is called hyperparameter, and the process of finding optimal value for the hyperparameter is called hyperparameter tuning. This hyperparameter and hyperparameter tuning is in reference to something that we'll be using further in the session as well. So for the parametric and the non-parametric values, or algorithms, the parametric models, they make certain strong assumptions about the data when they are working with the data. The data is assumed to be following a specific kind of distribution, such as a normal distribution and stuff. The logistic regression is an example of the parametric model. Now, the non-parametric model, they do not make any kind of assumptions about the underlying data, and they means that they do not assume that the data follows a certain kind of distribution. The KNN memorizes the data and classifies the new observations by comparing the training data. So this is what the example is, and how the KNN or the K nearest neighbor works. So keep in mind the image that you are seeing of the graph. So if we plot these points on the graph, we may be able to locate some clusters of or groups that are already plotted. And now given an unclassified point, which is a new point that we have introduced into the graph, we can assign it to a group by observing what group it's nearest neighbor belong to, means which the new data point is most nearest to. So this means that a point close to a cluster of points classified as red has a higher probability of getting classified as red. So for this, we for measuring this distance, a Euclidean distance is one of the most commonly used distance metrics, though there are certain other ones that we'll be discussing further. So for Euclidean distance, the mathematical representation of D0, 1, DO1 to DO2, the Euclidean distance can be given by x11 minus x21 whole square, where x11 and x21 are the values of the features of x1 for records 1 and 2 respectively, plus x12 minus x22 whole square, where they are the values of the features of x2 for records of 1 and 2 respectively, and whole square and a whole square root to the both the terms, a common square root to both the terms. And as said before, Euclidean distance is not the only distance that is used. Minkowski distance, Jaccard coefficient, and Gauss distance are other distance metrics that are used. Another example of a Euclidean distance, as you can see, for the x and y coordinates, the x2 minus x1 whole square plus y2 minus y1 whole square, the whole square root. So for implementing the K nearest neighbors for our Python implementation, the Sykitleraning dot neighbor module, sklearn dot neighbors module is used to import import the K neighbors classifier algorithm, which takes the sum of the these parameters. First is n neighbors, which is an integer type, the number of neighbors to use by default. And its default value is 5. Then there is a metric called string, where the distance matrix called Minkowski is the default. The available distance metrics in sklearn are discussed in the sklearn. Okay. So then weights, which is a string type. The default is uniform, where all points in each neighborhood are weighed equally, else the distance which weighs points by the inverse of their distance. Now, using the default for for creating our KNN or a K nearest neighbor model, we will be using the default values first. So our n neighbors will have the value of 5, and the metric will be having the Minkowski distance. So using the scikit-learn to import the K nearest neighbor or K neighbor classifier algorithm, then KNN underscore CLF will be our model, and fitting the model, you can get the short summary of the model and the parameters that are used. Now, drawing the curve, ROC curve for our model, we get the AOC score of 0.84. Now, K nearest neighbor, KNN, is we'll be using the draw CM or drawing the confusion matrix for our KNN model. So you can see the false positive and the false negatives over here, that they are comparatively more. Just a second. though it is an improvement from before, but still we can have a certain kind of improvement regarding the model. So when we get the classification report uh, about our KNN model, you can see that there is an improvement for the recall score of uh, y equals to 1, or the positive observations, which is 0.75. That which is a good improvement from 0.25 that we got for the our logistic regression model. So these are the scores that we get for our hyperparameters value of k equals to 5. So what will be the effect of changing the value of k, or what will be the most optimal value of k for us, or for getting our best model? So the Escalon's grid search mechanism, a brute force approach, which searches for a single or multiple hyperparameters where the model gives highest accuracy. So a grid search mechanism will be used, or the method will be used in order to find the k's optimal value. So this is called a grid search CV, which is a part of Escalon.model selection, which searches through a set of given hyperparameter values and reports the most optimal one. It does a k-fold cross validation for each value of hyperparameter to measure accuracy and avoid overfitting. The parameters that it takes are estimator, parameter grid, scoring, and CV. CV is nothing but the value of k in the k-fold cross validation. The estimator is the which implements the estimator interface, or the ML algorithm. Then parameter grid, a dictionary with parameter names as keys and list of parameter values to search for. Then scoring is a string type, the accuracy, which is a accuracy measure. For example, R2 for the linear regression models, the F1 precision recall, or ROC AOC curve for classification models. So we'll be starting with these values of the parameters, which is for n neighbors. We'll see the combination from 5 to 10. And for the matrix of distance, we'll be using the Canberra, Euclidean, and Minkowski, and see all the possible combination of hyperparameters, and see which is the most robust model that we can get from those combinations. So to measure the robustness of the model, each set of value will be evaluated by k-fold cross-validation. The accuracy measure reported will be the average accuracy across all the folds from the k-fold cross-validation. So creating the dictionary with hyperparameters and possible values for searching, the tune parameters, then configuring the grid search, then fitting the CLF model, which is the classification model that for the grid search is using the grid search CV on the train and the train split of the X and Y features. We get the value of 0.82 when we get the CLF dot best score. When we get this best score about the classification model, the score that we get is a 0.82 or 82.93%. And the best parameters that we get are Canberra and number of neighbors of equals to 5. So when we get the grid scores, you can see the way it works, and the report it generates for all the possible combinations that it works through. So in this, higher standard deviation could also mean that it is an overfitting model. Now we'll be discussing the Ansible methods. So ensemble method is a machine learning technique that combines several base models in order to produce one optimal predictive model. So ensemble methods are learning algorithms that take a set of estimators or classifiers and classify new data points using strategies such as majority vote. The majority voting could be based on counting simply the vote from each class, or it could be weighted based on their individual accuracy measures. The ensemble methods are also used for regression problems where the prediction of new data is simple average or weight average of all the predictions from the set of regression models. So in the image, you can see that the original set has been spread into a number of sets. Sorry, not n. Sorry, a certain number of sample set are created, and which are given to the different models. So, and in the end, those results are aggregated into one. So taking a simple or a weight average for regression, if the models are regression models, or if in case of classification models, the majority voting is done, where capital K and N that are used in the image, they are the number of features and the records of the original dataset respectively, where the smaller case K and N are used as number of features and records in the sampled set. We'll see why we have said the bootstrapped samples further. So when building the multiple classifiers, we usually have only one training set. So instead of using the same set for all the classifiers, we use the bootstrapped samples. These samples are randomly drawn with a replacement from the original training set and given to each classifier. Sometimes we also sample only a subset of features along with the observations. Each new data set contains a different mix of features. Data points not included in the particular sample are reserved for testing, then which are called out of bag records, and they help us evaluate the model's accuracy without needing a separate validation set. The process of bootstrapping samples from the original set to build multiple models and aggregating their results for the final prediction is called bootstrap aggregating, or bagging for short, where random forest is one of the most widely used bagging techniques. So we'll be discussing random forest now. So it's an ensemble technique of a decision tree, where each tree is built from bootstrap samples and randomly selected subset of features without replacement, which means every one of them is being unique. The decision trees are normally grown deep. The number of estimators or models to be used in a random forest can be tuned to increase the model's accuracy. And the decision trees are normally grown deep without pruning. So the hyperparameters that the random forest model are number of decision trees, number of records and features to be sampled, and the depth and the search criteria, which is the Gini impurity index or entropy being used as the splitting technique. So when we implement the random forest, we'll use the scikit-learn ensemble and import the random forest classifier from it. The estimators, the n estimators is the number of the parameters, and now we'll discuss the parameters. So the n estimators is the number of trees in the forest. Criterion, the function of measured to measure the quality of the split, which is Gini. It can be Gini or entropy. By default, it's Gini. Then maximum features, which is the number of features to be used for each tree. If int, then consider max features for each tree. If float, then max features is a percentage, and if used as int, then the features are considered for each tree, which is the max features into n features. And if kept on auto, the max features are square root of n features. If square root, then it's the same as auto. And for log 2, the max features get a log of n features with the base 2. Then the maximum depth of the tree is defined by the max depth parameter. Now, implementing the random forest classifier with our random CLF as our model, and fitting the model with the training set of X and Y. And if we get the summary of random forest classifier as such. When we draw the ROC curve about the random classifier model, we get the AUC, or the area under curve, score of 0.86 or 86%, which is better than the KNN model of 0.80 that we got. So, 0.86 is a good score, but we still want to see that whether we can improve the model or not, and how can we improve. So we can improve it using the grid search CV, but one thing with the grid search is that it can be time consuming. So the only parameters that we'll be considering are the max depth, n estimators, and the max features, and their values of 10 or 15, 10 or 20, and square root or 0.2, and use a small set of values for the search. So for the tune parameters and giving the values for the max depth, n estimator, and the max features, then initializing the random classifier model, giving the tune parameters as one of the parameters, and then fitting the model, we get the summary of our model with its parameters. I have not printed the whole summary over here, but we'll see it when we summarize the whole session. So when we get the best score for our CLF model, we get the score of 0.94 or 94%, and the best parameters for our model are the max depth equals to 15, the number of max features, keeping it as an auto, and the n estimators equals to 20. So the accuracy of 0.9413 AOC score is given by the random forest with 20 decision trees, and the maximum number of features as auto, and the depth of 15. So now we'll be getting the optimal values of these with the random CLF model and fitting the model on that. Whenever we fit the model, we get the summaries, and you can see the parameter values of them. Now, drawing the ROC AOC score curve, or the ROC curve, we get the AUC score of 0.94. Drawing the confusion matrix on the random CLF, on our random CLF model, you can see that the the false positive and the false negative values have been decreased now. So, and when we get the classification report of this model, you can see that the recall value and other metrics of precision, F1 score and stuff have been good as well. The recall value of positive classes is 0.81. So finding the important features or the most important features. Report of a random forest algorithm provides the most important features related to outcome variable by considering feature usage over all the trees in the forest. So how is that calculated? The feature importance is calculated for a feature by multiplying error reduction at any node by the feature with the proportion of samples reaching that node. Then the values are averaged over all the trees to find the final feature importance. So in scikit-learn's classifiers returns a parameter called feature importance. So we'll visualize these features now. So basically what we are doing is we are trying to visualize the features that are most impactful on making the subscription equals to yes. So we'll be using it we're starting with importing NumPy using the data frame for feature rank, then sorting the values of the feature rank with as ascending equals to false, meaning that the highest or the most highest values of the features will get to show first. Basically, that's the only reason why we use ascending equals to false. And then plotting the graph on that, you can see the top 5 features that are most impactful for making the subscription of the banking's term plan. So the top 5 features according to the plot are balance, age, previous campaign, current campaign, and the house loan. Having a house loan, yes, basically means that they have the house loan or not. So the importance score is normalized and shows the relative importance of the feature. The cumulative sum of features importance can show the amount of variance explained by the top 5 features. So we will use the pandas cum sum method that can be used to compute the cumulative sum of it. So feature rank is used for a cumulative sum of it. And you can see when we print the top 10 records, the top 10 records are being printed from balance, age, previous campaign, current campaign, house loan, yes, education, secondary, then marital status, personal loan, job type, and the marital status single. So important points regarding the random forest important features. The top 5 features provide 75% of the information in the data with respect to the outcome variable. This technique can also be used for feature selection. Random forest, being a black box model, cannot be interpreted, but it can be used to select a subset of features using feature importance criteria and build simpler models for interpretation. So now we'll be start our discussion on boosting. So boosting is a powerful technique in machine learning that improves the model's performance by combining multiple weak learners. It belongs to the family of the ensemble method, which leverage the strength of multiple models to create one strong model or more accurate predictor. The data scientist trained machine learning software called machine learning models on labeled data to make guesses about the unlabeled data. A single machine learning data, uh, a machine learning model might make prediction errors depending on the accuracy of the training data set. For example, if a cat identifying model has been trained only on images of white cat, it may occasionally misidentify a black cat. So boosting tries to overcome this issue by training multiple models sequentially to improve the accuracy of the overall system. Two most widely used boosting algorithms are adaptive boosting or AdaBoost and gradient boosting. So what are weak learners and the strong learners? As we have mentioned, the weak learners have low prediction accuracy. Similar to random guessing, they are prone to overfitting. That is, they can't classify data that varies too much from their original set. So if you train the model to identify cats as animals with pointy ears, it might fail to recognize a cat whose ears are curled. Then for strong learners have a higher prediction accuracy. Boosting converts a system of weak learners or combination of weak learners into a single strong learning system. For example, to identify the cat image, it combines a weak learner that guesses for pointy ears and another learner that guesses for cat-shaped eyes. After analyzing the animal image for pointy ears, the system analyzes it once again for cat-shaped eyes. This improves the system's overall accuracy. So for boosting, how it works is equal weight to data. When we start with boosting, at the start, each data point is given equal importance. We feed this data into the first model, often called as the base model. So this model makes the predictions for each data point. Now, adjusting the weight based on the errors that are made by the base model. After making predictions, we check where the model went wrong. Now, we increase the importance of the data points where the model made bigger mistakes. Also give more importance to the model that makes better predictions. Passing weighted data to next model. Now we send the adjusted weighted data to the next model in line and repeat and improve. Uh, we basically repeat the steps 2 and 3 again and again, and each time focusing on more on the mistakes of the previous models, and we keep doing this until overall errors are minimized below a certain level of threshold. So starting with a first technique of boosting called adaptive boosting or ADA boosting. It's one of the earliest boosting model developed. It adapts and tries to self-correct in every iteration of the boosting process. So ADA boosting initially gives the same weight to each dataset, then it automatically adjusts the weight of the data points after every decision tree. It gives more weight to incorrectly classified items to correct them from the next round. For the next round, it repeats the process until the residual error or the difference between the actual and the predicted values falls below an acceptable threshold. So you can use the adaptive boosting with many predictors, and it is typically not as sensitive or as other boosting algorithms. This approach does not work well when there are correlation among features or a high data dimensionality. Overall, adaptive boosting is a suitable type of boosting for classification problems. So after each classifier, usually a decision tree is trained. The classifier's weight is computed based on its accuracy. So more accurate classifiers are given more weight. The final prediction is based on the weighted sum of all the classifiers and is given by the formula of f of xi, where summation equals to k equals to 1 to k, alpha k into f of xi, where k is nothing but the total number of classifiers. Fk of xi is the output of the weak classifier k for input feature of set xi, and alpha k is the weight applied to the classifier k and is given, and alpha k is given by 1 by 2 into log of 1 minus epsilon k by epsilon k. Alpha k is based on the classifier's error rate epsilon k, which is the number of misclassified records over the training set divided by the total number of records of the training set. The final output f of xi is a linear combination of all the weak classifiers, and the final decision depends on the sign of this sum. So to implement the adaptive boosting in our in Python for our data that we are working with, we'll be discussing 3 parameters about it. The base estimator, the boosted ensemble is from which the boosted ensemble is built. The estimator should have the capability to utilize differential weights for samples, which are the decision trees or a logistic regression, for example. Then the n estimators, the maximum number of estimators at which the boosting algorithm is terminated. In case of perfect fit, the learning procedure is stopped early. By default value, it's a 50, and the learning rate, which ranks the contribution of each classifier specified by learning rate. There is a trade-off between learning rate and estimators. The default value of learning rate is 1. So to apply the adaptive boosting for our logistic regression CLF model that we created for the logistic with the use of logistic regression, the adaptive CLF being used for the adaptive boost classifier, and given the n estimator as 50 and fitting the model, we get the summary of the parameters that are used for, by the model. And when we draw the ROC curve of the model, this is the curve that we get for the area or the AUC score of 0.71 or 71%. Now we'll discuss gradient boosting. Gradient boosting is similar to adaptive or adaptive boosting in terms of sequential training. The difference between AdaBoost and the gradient boost is that it does not give incorrectly classified items more weight. Instead, the gradient boosting optimizes the loss function by generating base learners sequentially so that the present base learner is always effective than the previous one. This method attempts to generate accurate results initially instead of correcting errors throughout the process, like we saw for adaptive boosting. And for this reason, it can means the gradient boosting can lead to more accurate results. The gradient boosting can help with both classification and regression based problems. So gradient boosting is a sequential training technique used for both classification and regression problems. It unlike adaptive boosting, it focuses more on minimizing the errors. Each new model is trained to predict the residuals from the previous models rather than focusing on the misclassified examples. To minimize the error, gradient boosting uses a gradient descent algorithm. In each stage, adjusting the parameters of the models to minimize the loss function. And typically, decision trees are used as the base classifier in gradient boosting. And overall, the gradient boosting aims to generate accurate results by iteratively strengthening the model with weak predictions and minimizing the error using a gradient descent approach. Basically, let's say there are three models being used. And the first base model, its errors will be rectified by the gradient boosting, and those will be passed on to the further model, and that further model will also be rectified in to minimize the error and further passed on to the next model in line, where each of those models have a low or more minimization of the error than the previous one. So each model gets better as we move forward. So gradient boosting, mathematically speaking, f of xi equal representing f of xi equals to summation of k equals to 1 to k alpha in for alpha k fk of xi, where alpha k is the learning rate or the accuracy of the model k. So the following steps are used in the gradient boosting. Fit the first model to the data, y equals to f of f1 of x. Then fit the next model with the residual error, y minus f1 of x, which is f2 of x. Then the above steps are repeated until the residuals do not change significantly, and the final model is used to make the final predictions. So using the Ansible gradient boosting classifier for our gradient boosting, the parameters that it takes, the n estimators, which is the number of boosting stages to perform. The default value is 100, and the gradient boosting is fairly robust to overfitting. So usually a large number of estimators result in better performance. Then the maximum depth of individual regression estimators. The the maximum depth limits the number of levels from the root node in the tree. Then max features, the number of features to consider when looking for the best split. The applicable values are given in a random forest section. Okay. So we'll build our model with 500 estimators and depth value of 10. So we'll call our gradient boosted classification model as C, GBoost CLF, and when we fit the model using the train split of x and y, we get this summary of the parameters that are used by the model. When we draw the ROC curve for our model, we get the area or area under curve score of 0.98. The best metric, which is the best metric so far for all the models that we have built. But this score can also be due to the overfitting. So to check for the overfitting, we'll be using the k-fold cross validation or the 10-fold cross validation to check. So using the same parameter values, then using the CV scores for it, and then printing the CV scores and the mean accuracy and the standard deviations, we get the the respective values over there, where the mean accuracy is 0.96 and the standard deviation is 0.0093. So this is a robust model with 96.8% of a AOC score. And now we'll be building the confusion matrix on it. So for building the confusion matrix, you can see that the false positive and the false negative values that are which are 68 and 33. And when we get the classification report of this, we get the recall score of 0.94 on 94%. So the boosting algorithm also provides a feature importance based on how each feature has contributed to the accuracy of the model. So we'll be creating a plot on which are the most important and the contributing factors or the features which give us the most important features and the accuracy of the model. So this is something that we have done before also, and we are doing it for the gradient boosted classification model. So when we plot the graph, these are the values that we get. So you can see that according to the graph, the balance, age, and current campaign are the top features which have the maximum information about whether a customer will subscribe or not to the term deposit plan of the bank. So to summarize the whole session, we started with a bank's dataset, which was about the term term plan launched by the bank, and bank started a campaign, and bank wanted to know who which are the customers that are more likely to say yes to the or subscribe to the term plan and not. So we read the data set and printed few of the first 5 values of the data set, got the information regarding the data set, and when we got the value counts on the subscribed column, these are the values that we get, and which makes the data set that we have or that we are going to work with an imbalanced data set. So to work or to deal with the imbalanced data set, we discussed about the upsampling and downsampling. We upsampled the data set, which is basically increasing the minority to a certain point, and we increased it by the 2000, and which was and after that the new bank DF contained the ratio of 67:33 for no and yes. Now for and also we used a shuffle. We shuffled the data set so that it does not occur in a particular order. Then creating the X features. These are the X features that we have. One hot encoding the categorical features. These are the just creating the int value for X equals to yes, or X equals to 1, converting the X equals to yes to X equals to 1 basically. Then training the data set, splitting the data set, then creating a logistic regression model on the splits that we have created, and this is the summary of it. Then creating the confusion matrix, and this is the draw CM or draw confusion matrix custom method that we have used. And when we create the custom method confusion matrix, this is the confusion matrix that we get. for our present model. When we get the classification report, this is the classification report, and you can see the recall value of 0.22 for our current model. So now predicting the probability values for the test cases, and these are the top 5 values of the test cases that we get for the class 0 and class 1. Creating the test results DF, and assigning the probability values for the class level of 1, and printing the values. And for creating the area under the curve score, this is what we'll be using, and we get the value of 0.69. So for plotting the graph, we'll be creating a custom method of a draw ROC curve. When using the draw ROC curve on our present model with, just a second, draw ROC curve. This is the curve that we get, and you can see the 0.69 value over here. Now, moving further with the K Nearest Neighbour algorithm, which is a non-parametric algorithm, means that it does not make any kind of assumptions regarding the data. We create our model using the K and K neighbor classifier in the Sykitleraning dot neighbors, and fitting the model. These are the values regarding it, regarding the parameters that are used in the model. Then drawing the curve on the KNN model, we get the AOC score of 0.81. This is present in the curve in the graph as well. Now creating the confusion matrix and the classification report on the KNN model that we have created. This is the confusion matrix that we have, and this is the classification report that we get. And we get the recall value of 0.68 on our positive observations. So we'll be using the grid search for seeing the most influential optimal parameters for our model. And these are the parameter values that it uses, and using the CLF dot best score, this is the score that we get, which is 0.82 or 82%, and getting the best parameters, Canberra and the number of neighbors as 5 are the best parameters that we get. So now starting the discussion regarding the ensemble methods, we discussed the random forest, and we started building the random forest model. So building the random forest classification model and fitting the model on train and test on train split of the X and Y. These are the parameter values that it uses, and when we draw a plot on the random classification, a random forest classification model, this is the curve that we get, and this is the area AUC or area under the curve result that we get, which is 0.86. So we are looking to further test the accuracy or improve the model. So we'll be using the grid search for finding the most optimal parameters. Though time consuming, we'll be using these 3 parameters to work with. So working with these 3 parameters, these are the parameter values that we get, and for the CLF model, the best score is now 92%, which was 80 something percent before. So, and the best parameters that we get are a max depth value is 15, the max features square root or auto, and n estimators as 20. Now, building the final model with all the parameter values that we have gotten. These are the parameter values that are used, and drawing the ROC curve on it, we get the AUC score of 0.94. We get the AUC score of 0.94, which means that it is a robust model in a way. Now, drawing the confusion matrix on a random class, random forest model, and the recall value of for positive class is 0.81. Now, finding the important features that are or the most contributing features from the X. So when we plot the graph, this is the graph that we get, and you can see that balance age, previous campaign, and current campaign are some of the most influential or the important features. So using the cumulative sum and sorting in descending order to get the most valuable features first, and then printing the top 10 of it, you can see the features that are listed over here, from balance age all the way to the kind of job of a blue collar. Then using the boosting techniques, starting with adaptive boosting, we call our model ADS CLF, and the parameter values that it uses. Then drawing the graph on the ADS CLF, we get the AUC score of 0.69. For gradient boosting, we created the model GBoost CLF, the parameter values that it takes, and creating the graph using the GBoost, we get the value of 0.97, or area under the curve score of 0.97. You can see it over here. So using creating so because it's a high score, we want to make sure that whether it's not overfitting. So we'll be using the k-fold cross validation and having the case value as 10 over here, and printing the CV scores, the mean accuracy, and the standard deviation of the model. You can see the mean accuracy of 4.96 and a standard deviation of 0.012. So these are solid numbers, so it's not overfitting, and drawing the confusion matrix for the gradient booster classification model. This is the confusion matrix that we get, and we are getting really low values of false positive and the false negatives. You can see the recall value of 0.93 for our positive class. And when we see the most important features for most important features in terms of graph, this is the graph that we get. And even in a gradient boosting, the balance age, previous campaign, current campaign are the most important features that we get. So according to the current model, balance age and previous current campaigns are the important ones. So these are some of the references that were used for making this session or reading through with this session. Yeah, this is the end of session 6 in whole. And yeah, thanks a lot for listening. Thank you.
Yeah, thanks, Jamie. It's a great presentation, and we went through the advanced topics. You covered the various things, including KNN and what do you call the confusion metrics and all. It was a good one. Let's hope with this we probably may have one more at the most. I think Friday is the last one, right? Or you have
Yes.
anything? Yeah.
Yes.
Okay, so we'll discuss on Friday, and
Yeah.
thank you very much. And
Yeah.
I'll post the record soon. Okay,
Yeah.
let
Thank
me
you.
stop the recording right now. Just a
Yeah.
second.